Okay, welcome. This is an optimization program that I've been working on. The original name was ALPS. I called it a linear programming system, and then I got an email from a guy that I think worked at DARPA, and he said, "Is that the one that the DARPA uses?" And I said, "No, this is my own." So I just decided I better rename it. So I decided to call it TAMPA, Taming Mathematical Programming in APL. So. Now, what I'm trying to do is build up an app library for Dyalog, programs written in Dyalog. And a lot of people complain that there aren't a lot of libraries in Dyalog, so I'm trying to fill that gap if I can. And so my flagship product is TAMstat, which I've talked about in previous conferences. I've added a couple of new features over the past year or so. Non-parametric statistics, new analysis of variance designs, and theoretical probability graphics. So if you're interested in TAMstat, you can see me during the breaks, and I can give you demos of it and stuff like that. I've also have a couple of other apps in the pipeline that I've been developing over the years. One is called Adage, a Dyalog APL generated equation solver. I have another one called TAMstop, which I just renamed recently, Taming Stock Options. It'll do option pricing. And finally, we have TAMPA, which is Taming Mathematical Programming in APL. So you can kind of see a pattern here. I'm sort of creating a series of apps, and I call them the Taming series. I don't know if you're familiar with Bill O'Reilly, who's written a lot of books called Killing Lincoln, Killing Kennedy, Killing Jesus, and he has a whole bunch of the Killing series. Well, I don't want to kill anything, I just want to tame it. So what is mathematical programming? This is a term that's often used. A mathematical programming has it basically deals with optimization, and a mathematical program has three components. We have what we call a decision variable, which is, if you think of one example would be, if you're in business, you produce several products and you want to know how much of each product to make. And that's your decision. You have an objective function, which is a function of those decision variables. For example, what's my bottom line? What's my profit? And then a third thing, you would have constraints, which are resource limitations, and those are defined by a series of functions, and a limit here on the right. The B sub k represents the limited amount of resource that you have. So linear programming is a special case of mathematical programming where these functions are linear combinations. So, for example, here, the objective function, you have a bunch of coefficients, which could be unit profits, for example. And the constraints are all linear. Everything's linear combinations of everything. It makes life a lot simpler when you deal with linear. So I want to talk a little bit about linear programming in general. In linear programming, we can replace summations with matrix notation. So the matrix notation for a linear program is something like, you would say max C prime x, where C is a vector and x is a vector, subject to AX less than or equal to B. A is a matrix. I made that a capital letter just to emphasize that. So C is a vector of coefficients, and the objective function A, capital A, is a matrix of coefficients for the constraints. B is a vector of resource limitations, and X is a vector of decision variables. Well, we see matrices and vectors, and what do you think? APL, right? So I thought this was an excellent application to do an APL. So what does the syntax look like? Well, down here I have a little key indicating what's an array, what's a function, what's an operator, and what's a namespace. So we propose the following syntax for linear programming and also for nonlinear programming, which is in the future. So here's an expression, an APL expression. So a namespace is the max optimize CX subject to AX less than or equal to B. It looks almost identical to the mathematical notation. And you can see that some of these things are operators and functions and so on. Now, notice that A, this is the constraint matrix, and B is the resource limitations, and C, those are the three variables. C are the coefficients for the objective function. If we wanted to extend this to nonlinear programming, we would just replace C here with a function, an objective function, which doesn't have to be linear, and we can replace the A matrix with a kind of another function, and this would apply to nonlinear programming. Now, none of that's been developed yet, but I like to leave the syntax open for expansion. So, what's going on here? Well, you can see that these dashes underneath, this is a series of phrases which are based on, you can see that the operator, this X is an operator. The reason is you think X are the decision variables, but we don't know what they are ahead of time. So I kind of use some sleight of hand and made that into an operator, which kind of binds things together. So what's going on here? Working from right to left, this is the right argument. This expression becomes a function. It's an operator with left and right operands. It creates a namespace, and we just put data into it. This builds something called a tableau, which is what we use to do the actual calculations. And then the optimization runs the linear program, and we assign everything to a namespace. And if you want to further make it more English-like and readable, I can replace max optimize, this is an operator, with a function called maximize. So we just call that maximize or minimize. If you want, you might want to maximize profit or minimize cost. Let's look at it. I'd like to look at an example, a concrete example. So we have something called Blue Ridge Hot Tubs makes 3 models of hot tubs. Oh, thank you. Blue Ridge Hot Tubs, it makes three types of hot tubs. And Aqua Spa, Hydrolux, and Typhoon Lagoon. The unit profit on each is $350, $300, and $320. And we have some resources here. Each hot tub requires 1 pump, and we have 200 pumps available in our warehouse. For labor, it requires 9 hours of labor to build an Aqua Spa, 6 for a Hydrolux, and 8 for a Typhoon. And we have 1,566 hours available for that. And then we also need tubing, so 12 feet, 16 feet, 13 feet for each corresponding, and 2880 feet available. So we want to, given the resources that we have, and the limitations and the objective is our profit, we want to maximize our profit. How do we figure that out? And we can use mathematical or linear programming to do that. So we have a couple of questions we want to ask ourselves. So here's, in building a hot tub, we want to know how many hot tubs of each type should Blue Ridge produce? That's the main question. That's what we're trying to find out. But we also have a couple of peripheral questions we'd like to ask. So let's see. What is the maximum profit? Okay, that's not that's the bottom line. How much additional profit can we realize if we get additional resources? How much additional profit can we get by getting additional resources? And what are the costs of deviating from the optimal solution? So if we deviate from the optimal solution, how's that going to affect our profit? So let's formulate this in mathematical notation. So we're going to let X1 be the number of Aqua Spas to produce, X2 the Hydroluxes, and X3 the Typhoon Lagoons. So our objective is to maximize this equation, 350x1 times a number we produce, 300x2 plus 320x3. That's our objective function. And subject-to, so since we only have 200 pumps, we just add up all three of the hot tubs. That has to be less than or equal to 200. And this next one is the labor constraint and the tubing constraint. And of course, we also have to say that the x's have to be, you can't make negative hot tubs, so it has to be at least 0. So we're going to set up some vectors and matrices. So we have x is a vector of the decision variables. C are the coefficients for the objective function. A is the constraint matrix, and B are the constraint limitations. So 215, this is the limitations on each of the resources that we have. So we have four things here, three vectors and one matrix. Now in standard mathematical notation, they treat vectors as one column matrices, and you have to transpose them. So that's why they say C prime, that prime is a transpose. We don't have to transpose vectors in APL, which I think is a marvelous thing that mathematics hasn't really caught on to yet. But so in TAMPA, we're going to set up the objective coefficients. So I'm just going to assign that to C. The constraint coefficients, I just create a matrix, the A matrix. And then the resource limitations is the B vector, okay? And so now I just type in this expression. NS is assigned maximize CX subject to AX less than or equal to B. Reads exactly, almost identical to the mathematical notation, except I don't have to transpose the C vector. So one of the results is ns.decision. It says, okay, make 122 aqua spas, 78 hydroluxes, and don't bother making any of the typhoon lagoons. And that's your optimal thing, your optimal solution. And, I forgot to put it, ns.objective. I should have put that in. I forgot to put that in. The objective will tell you it's like around, it will tell you the total profit. I think it's like $66,000. But then we have some other things like something called shadow prices. It says each additional pump available contributes, if I get an extra pump, it's going to contribute an extra $200 to profit. If I get an extra hour of labor, that'll tell me it'll give me almost $17 of profit. And I have excess tubing left over, so it doesn't, extra tubing is not going to give me anything for profit. And then we also have something called reduced costs. It says the zeros for the first 2 hot tubs, it says if I make additional hot tubs, it's not going to affect my bottom line. But if I make each typhoon lagoon that I make, I'm using up resources that could be more profitable to the other hot tubs. So I'll lose $13.33 for every typhoon lagoon that I make. So this is kind of good for if you're in business and you want to see if you can optimize your profit. So anyway, what's going on under the covers? This is the expression. On the far right, AX is less than or equal to B. And anyway, I don't want to spend a lot of time on this, but all I'm doing is populating this namespace with values. And so I think I'm going to skip over this because I want to get to the graphical user interface, okay? Because that's what. So we're using something called Abacus, which sort of generates a graphical user interface using the HTML renderer. And I think Norbert's going to be talking about that later. So I want to kind of do a little demo of that. So let me go to, and I guess I can. I'm going to run hot tubs. So I create a grid here. At the top, you can see these are the, I've pre-populated this so I don't have to waste time typing it in. But you can see it says maximize, and then we have the number of aquaspas, hydroluxes. The decision is in green here, and that hasn't been populated yet, and the total profit here is in the blue. And then these, you can type in whatever the unit profits are in here. And then down here we have the constraints, pumps, labor, and tubing. And you can see I put in the coefficients here. And then on the far right are the available amounts available. The relation is less than or equal to. And so what I'm going to do is I'm going to hit optimize. And it will do the calculations, put in the, you can see 122 aquaspas, 78 hydroluxes for a total profit of 66,100. So that's how that works. Now, one of the things you might want to do is to add or delete constraints. So, okay, thank you. So for now, this include, I'm trying to replace these with checkboxes. I haven't got there yet, but we're doing that. We're going to try to do that with the renderer. What I can do is change, let's say I have extra pumps and I don't need to worry about the pumps. So I'm just going to change that to 0. So it says don't include that in that constraint. Let's see what happens. And so I can now optimize that. And notice that now I can make 108 aquaspas, 99 hydroluxes, if I don't have to worry about the number of pumps that I have. And my total profit goes up to 67,500. So that's one way to add. So I can delete that constraint. Every time you delete a constraint, your profit usually is going to go up. Now, let me put this back in. I'm going to put this constraint back in. And now I want to add, let's say I want to add a constraint. So I'm going to hit add constraint. And it adds another row, okay, in the grid here. And now this new constraint is a budget constraint. So I'm going to call this material cost. And let's say the cost of actual materials is $600 for each of the aquaspas, and $500 for the hydroluxes, and $400 for the typhoon lagoons. And I have $110,000 available, and so now I hit optimize, and you can see that now we can start making a few typhoon lagoons. And you'll notice here that these numbers are not integers anymore. So there is another branch of mathematical programming called integer programming, and you can restrict that to integers. And I don't have time to show that now, but you can change that so that you can deal with integers. Now I have another. I want to do another demo here. Actually, let me show you just briefly the run TAMPA function. What's going on here is you can see that I'm calling this program called Abacus, and I think Norbert's going to talk more about this. But it's bringing up, we can put in headers and titles and generate, we generate a grid, and that's kind of how all that works. Just want to show you that I have another program which is a minimization program, and this one is the weed whack. This is a make or buy problem, so I'm going to do something with a weed whacker. And so here's another program. Again, I pre-populated it. And we want to decide, M1 is make how many, we have two types of weed whackers. They're gas and electric. And we want to know how many to make and how many to buy, because some we manufacture them, but we also buy some too. And these are the costs involved. So we want to minimize the cost. So this is a minimize problem. And this is production hours, assembly hours, and packaging hours, and these are the limitations. And this is the consumer demand. We need to produce 30,000 of type of the gas and 15,000 of the electric. And then I can go ahead and optimize that, and it says, okay, I want to make 30,000 of the gas, 10,000 of the electric, and then I only want to build. I need to buy 5,000 of the B2, which is the electric. So this is a minimization problem. You'll also notice that in the relation column, I'm not always using less than or equal to. You might have greater than or equal to or equal to. And so the right operand to that X operator doesn't always have to be a relational function. If I'm actually creating a train. So it would be equals, comma, less than or equals, comma, less than or equals, comma. And I create a train, and I just put that in there. So that's another feature that I'm allowed to do. This third one is an example of integer programming, and I just wanted to mention that briefly. We have to hire lifeguards, and we need for each day of the week, we have a minimum number of lifeguards that we need. And so we generate, this is the linear program that we have. And so I had to, I'm creating some data here to generate, here's an example of a function train that I can assign directly to this namespace that I just created. And if I run the LP on it, and this is a cover function for the linear program, I get non-integer results. But I have another function called IP, which is the integer program, and if I run that, I get integer results. And that I have another program in the pipeline that does that. And the objective is that 24. We need a minimum of 24 lifeguards to hire in order to fulfill that. So in conclusion, basically there are different optimization techniques, and they can be extended to the following: linear programming, integer transportation problem, and which I didn't have time to show, and nonlinear program, which is not yet in development. We can use HTML renderer via Abacus to generate the user interface. I've been able to insert and delete rows and columns. I want to use checkboxes and drop-downs. I haven't really implemented those yet, but that's sort of the plan. And I have a website, www.tamstat.com. So if you want to, you can get information about Tamstat there. But also I have a paper called Optimizing with Defined Operators, which you can link to. If you go to tamstat.com, there's a little item on the left that says Papers, and if you click on that, you can get access to the paper if you want to, if you want more details about it. So I think I'm just about out of time. I can take questions if anybody has any.